Today I'll show you how we can automatically infer the model for stateful network functions. So the network today contains a wide range of complex stateful network functions such as firewall, load balancers, IDS, and nets. Note that these NF can come from many different vendors. As a concrete example of stateful NF, let's consider a stateful firewall that implements the following policy. External packets are only allowed on previously established TCP connection. Effectively, what this firewall is doing is keeping a connection map that stores per connection state for each active connection. So let's look at this policy in action. Host A wants to establish a connection with B, so sends a SYN packet, which is forwarded by the firewall. B responds with a SYN ACK, followed by A responding with an ACK packet. So at this point, the connection map registers that connection from A to B is established. What that means is that when B sends a data packet to A, that will be passed by the firewall and not dropped. Now let us consider another host C that wants to establish a connection with A, so sends a SYN packet, but as A to C, the connection is not established, this packet will be dropped by the firewall. Now, given our current network are composed of such stateful network functions, operator questions whether my policy is implemented correctly by the network, or whether we should check the NF before onboarding to the production network. To do so, operators rely on testing and verification tools, such as VMN, SIMnet, and Buzz. However, these verification and testing tools today require having the models of stateful network functions, and they use the model to guide the generation of verification proof, testing, and onboarding process. Unfortunately, today these NF models are handwritten based on manual investigation, and as we will see very shortly, they have a number of issues. First, they're likely to be very inaccurate, affecting the result of testing and verification tools. So suppose I'm the network operator, and I want to check whether my policy is implemented correctly using a testing tool called Buzz. In this specific example, this tool Buzz takes a handwritten firewall model as an input. In running the tool Buzz, surprisingly, we found that the tool flagged that the policy is violated, as the output of the handwritten model did not match that of the real firewall. However, we find that the real firewall is actually adhering to the intended policy. So we dig deeper into the issue and found that the root cause of discrepancy, that is the error in the tool, was because the handwritten firewall model did not reflect the true firewall implementation. Specifically, the real firewall was checking the three-way handshake, whereas the handwritten model was checking for the SYN and the SYN ACK only. Second, these handwritten models often assume a homogeneous model across different vendors. But if you look at these three very simple packet sequences, the firewalls from different vendors react very differently. So having shown the limitations of handwritten model, the goal of our project is to automatically infer the behavior model for stateful network function given a configuration. Specifically, given an NF with a config, we want to output a model that describes the input and output behavior of an NF. Specifically, we'll use a finite-state machine, or FSM, to denote a model. As shown by prior work, it's a natural abstraction to capture stateful behavior. The resulting model can be used by downstream network testing and verification tools. So having shown the motivation, the goal of our project, let's move to what makes the problem difficult and what are our insights to address them. So at a high level, there are two challenges. The first, there is a large space of configuration, and naively enumerating all possible config space is infeasible. Given a configuration, inferring the behavior model for stateful network function itself is also a very difficult problem. And not just that, NF can modify packet headers, which make the problem more difficult than it already is. Let's tackle the first one. Specifically, there are 3 factors that lead to combinatorial explosion in the configuration space. First, a configuration can take many number of rules. Within a single rule, there are IP and port fields that take large sets of values, like 32 bits for source IP, for instance. And they also take ranges, like -16 for IP prefixes or wildcard for ports. I'll show you how we tackle one by one. So to motivate for our own approach, I'll use the naive solution. So suppose the config is composed of n rules. There is essentially 2 to the n possible configuration. A naive solution would say, why not enumerate the model, getting the model for every possible configuration, which is clearly infeasible. So, but what if we can get a model, suppose we have some means to get a model for each concrete rule. If we have that, and if we know the process order of how the rules are parsed by an NF, then we can logically compose the model for individual rule. So I'll give you an example. In the case of first match, where the first matched rule is applied, we can do if packet matches rule 1, apply model 1. Else if packet matches rule 2, and so on. So far, I established that we need a model per rule, but a rule also has a large search space due to IP and port field. Let's see how we tackle that next. Suppose I have 2 rules, where only difference in those 2 rules are the concrete value used for source IP. One takes 10, and the other one takes 12. But what we observe is that the resulting model, they're logically identical, except the concrete value used for the source IP. That suggests that we can learn a symbolic model by abstracting away the IP and port field, right? So that means once we get a new config, we just have to substitute the corresponding value to our symbolic model, and this eliminates the need to infer the model for entire IP port space. But what about IP port field taking ranges now? Now it takes -16. Source IP and both destination takes -16. So for now, let's assume that the NF keeps per connection state. That effectively means that each connection is subject to independent packet processing. That is, given 2 distinct connections, their states do not interfere. So if we know this information, what we can do is that instead of generating all IPs within that range, we can just learn a symbolic model using just 1 connection in that range. And then what we do is that at runtime, we can instantiate to get an ensemble of FSM, where each model in Ensemble is a model for each connection. So effectively, instead of viewing a rule as keeping just 1 FSM, it's keeping an ensemble of FSM. So to quickly summarize, a config to handle many rules, we proposed using the compositional model. To handle IP port fields, we are going to first learn a symbolic model, and then at runtime instantiate an ensemble of FSMs. So now let's look at how we can infer the NF behavior. There are 3 sub-challenges. First, we need to actually infer the symbolic FSM. Second, we need to infer the state granularity. So for now, until now, we assume that the NF keeps per connection state, but NF can keep like per source state, per destination state, cross-connection state, where depending on the different types, how we instantiate an ensemble may be different. Lastly, we also need to handle dynamic header modification, which makes the problem more difficult than in this talk, I'll focus on the first 2. So let's look at how we can infer the symbolic FSM. So recall that our problem formulation is that we want to output an FSM for the NF with a configuration. What we observe is that there is a classical algorithm in learning theory called L-star algorithm that does, given a black box system, it will output an FSM representation of the black box. So what we can do is that we can leverage L-star as a starting point to infer the FSM. Even though there will be some practical challenges in applying L-star, but before I go into discussing that, I'll give you a brief background on the L-star algorithm. So at a very high level, L star takes input alphabet as an input, which is a set of input symbols that the black box takes. So in this case, it's A and B, right? So given this input alphabet, L star generates sequences like AA, ABA, ABBB, probes the black box, records the output, and use that input-output pair seen so far to infer the hypothesis FSM. And at some point, it queries an equivalence oracle for counterexamples. And we'll use that counterexample to refine the hypothesis FSM further and further. And this process of refinement is going to repeat until there are no more counterexamples found. The output is the FSM representation of the black box. So there are practical challenges of using L star for an NF. First, we need to generate input alphabet, which is effectively the entire space of IP packets in our case. We also need to classify an output of an NF, as well as building an equivalence oracle. In this talk, I'll focus on the first two, so let us look at how we can generate input alphabet. So as usual, the NF takes one rule that with the source IP and destination IP. A naive solution would say, why not exhaustively generate input or randomly generate input? The first one is clearly infeasible, while the second one is inaccurate because it will not explore the relevant state space of an NF. What we observe, though, to exercise a rule while handling the large traffic space is that we can generate packets using just IP and ports that appear in the rule. And in this particular example, that will be A and B, right? So using A and B, we'll generate packets for all interfaces. And then we can optionally prune them based on the reachability. So if I know that source IP of a packet entering from the LAN cannot be a public IPv, I can prune them out. Finally, I can plug in relevant packet types. So in the case of TCP, there will be SYN, SYNAC, ACK, FIN, and so on. Now, how do we classify an output, right? While this sounds very straightforward, there are certain nuances that we had to consider in building Alembic. First, we need to configure the timeout to classify output or mark the packet as a drop. Second, we need some translation layer to translate back and forth between symbolic and concrete packets. So please refer to our paper for more details, as well as how we build an equivalence oracle. So let's look at how we can infer the state granularity to tackle NF that may not be keeping per connection state. So at a high level, state granularity refers to state variable, like set of IP ports that the NF uses to keep state. So I'll give you a high-level different types of state granularity we consider in this work and their intuitive definition. So when I say NF keeps cross-connection state, effectively, all connections share the same FSM. Per source state NF means that for each source IP, there is an FSM. And the similar logic applies for per destination as well as per connection state. So effectively, you can view this state granularity as a key mapping to the corresponding model in an ensemble representation. So how do we infer the state granularity? The high-level idea is very simple. So suppose I configure two connections to have different source and different destination IP. And then I check, do they affect the same FSM, leveraging our L star-based workflow? If they do, it's keeping cross-connection state, as there's no overlap in the source or destination. If not, I do the similar test, but this time using the same source IP. If they affect the same FSM, it means the NF keeps per source NF. It could be keeping cross-connection NF, cross-connection state, but we already eliminated the choice from our prior decision-making process. So the high-level takeaway here is that we can use these independent assumptions across connections to construct test cases to distinguish different types. So far I showed you how to infer the symbolic FSM as well as infer the state granularity. So that brings us to the final workflow. At a high level, it's composed of two stages. First one is the offline, which need to run only once per NF. we can afford few hours to few days for this offline process. It takes NF as an input, the vendor documentation describing the types of rule that NF can take, as well as packet types. In the case of TCP, SYN, SYNAC, and so on. We will then generate a set of rule types where each rule type is associated with a different runtime behavior. In the case of firewall, it can be firewall accept rule and a firewall deny rule. And then for each rule type, we are going to leverage the FSM inference module to infer the symbolic FSM as well as the key using the key learning module. The output is the database of a symbolic FSM and the key for its rule type. Now, in the online process, given this database and the concrete configuration composed of multiple rules, we will first match a rule to a corresponding symbolic FSM and instantiate an ensemble using the key. The output is the logically composed version of such ensembles. Let's look at the evaluation. There are 4 points we want to make. That first one is our models are accurate. We can find interesting cases across different vendors. Our workflow is scalable, and our models increase the accuracy of testing and verification tools. In this talk, I'll focus on the first 3. But before I talk about accuracy, let me briefly describe this setup. So what we first did is that we took Alembic and modeled click-based NF, where we know the exact ground truth. And we took that tool and applied on a real NF, spanning 4 different vendors of the type firewall, load balancers, and net. We used 2 packet types. First one is the correct sequence, which is essentially standard TCP packets. The second one is the combined sequence, which combines it with packets with out-of-window packets to see how the NF reacts to out-of-window packets in the presence of out-of-window packets. Let's look at the accuracy. For real NF, you don't have the ground truth, so we designed complementary testing methodology. We generated configuration ranging from 1 to 100 rules and generate packet using 20 to 300 packets. So in our definition, accuracy is the percent match between the model prediction as well as the real NF. Using iPerf testing, we show 100% accuracy. Then we did random packet testing, where we chose IPM ports in a random manner. We see 99.8 to 100% accuracy. The interesting one is the rule activation testing, where we chose IP port to activate one rule. We see 95 to 100% accuracy. Note that 95% comes from a firewall model that was modeled using out-of-window packets that has more than 200 state. So let's look at what are the interesting findings that we found using Alembic. So let me compare the first, firewall, pfSense firewall, and a proprietary NF firewall. First thing we looked at is what is a sufficient packet sequence such that external packet can send TCP traffic to an internal host. We find that for pfSense, the SYN from internal is sufficient for external to send TCP traffic. For proprietary NF, it's SYN and the SYNAC. Both results were surprising because we expected the entire 3-way handshake. Second, we found that the proprietary NF has 79 states for firewall, which is much bigger than 2-3-state abstraction that handwritten models have. And both of them implement default drop policy. Let's look at Untangle firewall, which is even more interesting. Unlike the other 2, it implements a default allow rule and also is connection terminating in a very interesting way. That means the first SYN from internal is allowed, but for the second SYNAC, the firewall itself replies with an ACK packet, terminating that connection. When it gets the real ACK, it's going to drop to prevent duplicate. So what are the takeaway by looking at 3 different firewalls is that every firewall we modeled was vastly different from one another. And the real FSMs are much more complex. Like one is connection terminating, the other one has 80 states. That's why we need Alembic-like tools to model NF. We also have other findings. Firewall with incorrect sequence have 257 states. We find a lot of firewalls do not handle out-of-window packets correctly. A lot of them are let through. We find load balancings are done different ways. HA proxy does it in a connection terminating way, whereas pfSense load balancer is exactly like a destination NAT, rewriting IPM port for every packet. There are more findings in this paper. For scalability, as we increase the number of rules, we are going to see increase in the runtime. But for a config with 1,000 rules, we can respond within 5 seconds. So there are certain limitations and assumptions we make. There are certain assumptions regarding configuration. We assume at most one rule is applied. States across different keys are independent. We assume that we can learn a symbolic model by sampling some representative samples. We also make certain assumptions in the NF action. We specifically model only TCP-relevant behavior, where the NF can either modify IP port or forward or drop packet. We do not explicitly model temporal behavior. We only support 5 types of state granularity. The interesting future work, direction for future work is handling more complex NF beyond packet-in that follow packet-in and packet-out semantics. So to conclude, network testing and verification tools today require NF models. Generating them by hand is tedious, and their models are inaccurate. That's why we proposed Alembic, which can infer high-fidelity NF model given a configuration. Our evaluation shows that we can find implementation-specific differences. Our models increase the accuracy of testing verification tools. Our workflow is accurate. No, our workflow is scalable. Our models are accurate. And with that, I would like to take your question. Thank you.
Yeah.
Okay. So very, very interesting work and very difficult problem. You already took away one of my questions because you put it in future work, and that was about how do you deal with temporal issues.
Yeah.
But I was wondering if you can tell us a little bit about accuracy. I know that you said it in the paper, but in particular, right, it seemed that where this model, your system, is the most useful is where the state machines or the rules are just so many of them that it's difficult for a human to do that, will give you the ground truth, right? So how did you approach testing accuracy for these more complex models? Thank you.
I see. So in terms of accuracy, as we do not have the ground truth, we had to design some complementary way to test the accuracy. So we chose packet in a way to exercise the rule. Specifically, so essentially, we were generating like some sort of pathological TCP sequences where you don't see such sort of a packet sequence in a normal TCP establishment or in the teardown process. In an attempt to exercise the 100-state DFAs we found. Yeah.
Okay, next question.
So thank you for the talk. It's very interesting. I think my question is related in the sense that since you treat the NF as a black box, so do you require that there's operators to configure it correctly before you infer it? And then how do you make sure that operators know how to configure it correctly? Because this is more like a chicken and egg problem, right?
I see. So when we do a modeling process, we don't have any notion of correct or incorrect behavior. So what we are taking as an input is the set of rules that the NF can take. And given that rule, we are going to output a model. So in that sense, there is no notion. As long as the operator can configure the fields in a rule, then...
Yeah, maybe let me elaborate a little bit what do I mean by correct configurator, right? So because the behavior of the NF in some way depends on the runtime environment. For example, you can run the NF in a VM, and I can configure totally different IP table rules in the VM. That has nothing to do with the NF. And since you are inferring it as a black box, in some way your finite-state machines actually describing the entire system, not only the NF behavior, right? So how do I know the operators know how to configure the underneath rules so that it doesn't jeopardize the NF and let the NF operate in the correct way?
I see. So I think the best way to answer the question is we assume that we are given a set of interfaces that the NF is configured with. And then the rule is usually applied on one interfaces, but we don't assume that a priori when you do the modeling process. So as long as those things match between the operator and the person who's generating the models, then there shouldn't be a problem. Right. Yeah.
Okay, the last question. Yeah.
Sure. We'll be quick. Nodir from UBC. Excellent work. I liked it. So my question was following the chicken egg problem, where you output a model based on the input config, right? But input config, let's say, does not have subset of config. For example, if it is NAT, you are not supposed to translate anything from 10.0.0/16 subnet. So that's not part of my NF.
Right.
And your model will not include it. Is it right?
Yeah, so I guess I didn't talk about it in this talk, but we are required to have something called configuration schema that describes the types of rules and then the data type for each field that the NF can take. So that means if certain subset is excluded from our input, then we should exclude that when we generate a symbolic model. But if somebody tells me that you should probably model separately using that subset, then you can plug in and get a model for that specific subset. So essentially, we are not treating all the IP port range in the same way. We are like classifying into two types and learn a model for different types.
Okay, thanks.
Okay, let's thank the speaker.